recording, and soon I'll be able to share what we have recorded on YouTube. So yeah, Ian, our leader, you may take over.
Okay, guys, good morning. How are you? I think we can present what we have, share whatever you have, and then Doctor will see the recording. I think I'll be the one to start. Yeah, and since we are six, we can take, I think, like 8 minutes each or 10 minutes. Is that okay?
Yeah. Also, anyone, feel free to unmute yourself and say something. You can also use that. You can also use the chat to say whatever you wish to say. And yeah, Ian, I believe we can do that. It takes 8 minutes. Yeah,
All
Ian.
right, let me start.
But before you start, I think let's get confirmation from everyone if they're able to hear us. Tracy, Mark, Joy, Estin, are you guys able to get us?
Oh, yes, I can hear.
Yes, we can hear you.
Okay, that's a confirmation from Tracy and Mark. And Joy has texted. Estin, are you able to get us? Okay, I haven't got any reply from Estin, but hopefully he can get us. And whatever parts he missed, he can always get from the video. So yeah, Ian.
Okay, I think we can go ahead.
Yeah.
Okay, just a minute as I show my screen. All right, you guys can see this.
Yeah, I'm able to view your screen.
All right. Uh, just change this. All right, so last time I talked about the state of a qubit, and that was the intro of quantum computing. And we got to know what a qubit is and that it can be in two states at the same time, and it helps in very complex calculations. I also said quantum computing can be used in artificial intelligence and also other sectors. So today we're going to look at quantum logic gates. Yeah, and they enable us to do a lot, such as quantum information and quantum teleportation. They are similar to classical logic gates, but the difference brings out the potential of quantum computing. So before we go into quantum gates, let's start with classical gates. So yeah, classical gate takes in an input and brings out an output. So the input can be voltage high or low, 0 or 1. That's for the classical computers, the normal computers. Yeah, so last time we did discrete math, and yeah, there were some things we did about you remember these truth tables. Yeah, they also represent logic gates. So there are very many types of logic gates, not gates, and, or, nor. So not gate takes in an input and then inverts it. It gets one and it gets zero and puts one. Gets one, puts zero. The AND gate takes two things that are true, and if they are both true, then you get true. Yeah. For an AND, it combines an AND and a NOT gate, and then we have an OR gate, which takes either. It takes one. If there's a one, it's true. Yeah. So there are very many types of gates, and they can be combined to do very many things like half and full adders, which make addition and subtraction. And that's the basic operation of a CPU. Okay. So those are classical gates. So quantum gates are okay. A quantum gate. We shall start with a quantum NOT gate. So they're very similar to classical gates, but there's a difference, and that difference brings out the quantum capability.
Man,
So yes.
I don't know if it's intentional. It's like you're stuck on the first slide.
Oh, I'm stuck on the first thing.
I don't know whether I don't know if that was intentional or
Oh, yeah, I think I had gone full screen. Sorry about that.
okay.
Okay, yeah. All right, let me just keep it like this. So yeah, that's a simple gate. Takes in input, high voltage or low, 0 or 1, and you get an output. And then there are classical gates. And there are very many types of classical gates, not gates, and, or, nor. Yeah, and they do these operations. So you can read more about them online. But I just brought this so that we could bring in more about quantum gates. So quantum gates equivalent to classical gates. Yeah. So the first one is a quantum NOT gate. So it takes the state 0 and turns it into state that gets state 1. Yeah, so it just inverts. It's like this one here, the classical gate. Yeah. So it's represented with an X. Yeah, you can see this X here. And it turns one state into the opposite. So you get naught. This equation is a quantum equation, the superposition. Superposition means two states at one time. And yeah, the X also represents the NOT gate, which is an identity matrix. Guys did linear algebra. So remember this stuff just does the inverse. So today I'm going to talk only about the quantum NOT gates, and you can go and dive deeper into it. And just to end this, there was something we were talking about maintaining of the quantum state. This means the equation of quantum state. So due to decoherence, which means that the system loses its quantumness, which means being in two states at once, like superposition and entanglement. This is because we're dealing with photons, and any slight change in the atmosphere, like vibrations and electromagnetic change, can lead to change of the quantum state. That's why it's hard to keep them in that state, and that's why they keep them at low temperatures. Yeah, seen those big machines. So today they're using fiber optic to transmit light photons, which are necessary in quantum computing. And earlier on, they used the neutrinos wire, but they failed to use it because it could not easily interact with other photons. So in the next lesson, I'll talk about the Hadamard gate. Yeah, this is also in linear algebra, and that's where I want to end today. Thank you.
Uh, Hey, and thank you for telling us about the quantum gates. I think I'll go next. Then anybody else who's ready can follow after me. I hope everybody is able to see my screen.
Yeah.
Okay. So today in linear algebra, we're going to look at the whole essence of linear algebra is solving a system of linear equations. So today we're going to look at how to solve these three equations, 1, 2, and 3, using using elimination and back substitution. I'll start off with elimination. Uh, we'll look at when it succeeds, then we shall look at when it fails, and finally we'll look at back substitution to get our values of x, y, and z. So to start off, we'll start with elimination. Let me just write this question. Let me just write the values of this equation. Oh, actually, let's first look at how to represent this equation as a matrix vector multiplication. To represent this as a matrix vector multiplication, we simply take these columns. Let me pick a different color pen. So we look at each of these columns, this, this, and finally the right-hand side that. As a matrix, as a matrix vector multiplication, this would look something like this. We have the first x, that 2, the 3. And since we have no x's here, we'll have replace it with a 0. Plus the y's, that's a 2, 8, and 4. And then we have our z's, which is 1, 1, 1. Equals to our right-hand side vector, which will be, which is 2, 12, and 2. This is our this is our this is our answer vector B. We're trying to combine this x, this y, and this z to get this vector B. The x, y, and z represent the amounts at which the amounts of these vectors we need, such that we get our final vector B. And this can be represented as this as a matrix vector multiplication: 2, 2, 1, 3, 8, 1, 0, 4, 1. That's our matrix. The transformation we have to apply on x, y, and z, such that we get the right-hand side vector 2, 12, 2. So that's how we can represent this system of linear equations 1, 2, and 3 as a matrix vector multiplication. We have our matrix A multiplied by our vector, let's call it x. Let's call it x equals our vector B. So let us look at how we can find the values of x, y, and z using elimination. Using elimination and back substitution. The first step is we have our values. We have the equations 2x. Let me put here plus 0y 0x. I don't think this is correct, but just to have it complete, let's have 0x there. We have our we have our three equations. I'm going to write them this way, leaving out the x, y, and z. 2, 2, 1, 3, 0, 8, 4, 1, 1. So I hope we all know this stands for 2x plus 2y plus x plus z. For simplicity, I'm just going to leave the variables out. Then I'll introduce them later when you have a much simpler equation. I hope everybody's okay with that. All right, let's proceed. So our first step of elimination is to subtract the first equation. Our first equation, this, from this equation, such that we eliminate this x, this 3x. And also to subtract this from this equation, such that we eliminate the x. But of course, we won't need to do that for this particular scenario because this x is already a 0. So we have to, I'll put some side work. We have to multiply these equations by some. Let me just confirm that these are correct. Yeah. So we have to multiply these by some amount such that this becomes a 0. So for our first equation, we multiply it by to make this a 0. If you can get this as 6, turn this into a 6 and this into a 6, we can subtract this and get a 0. We multiply this entire equation by a 3. We will have a 6, 6, and a 3. And then this, when we multiply it by a 2, we have a 6. We have a 6. This becomes, what does this become? 2 times 8, that's a 16. And this is a 2. Such that now when we subtract this, we get a 0 here. We get a minus 10. We get a 1. So this kind of becomes this this line will become a 0 minus 10 and a 1. Then we also have to do the same for this 0, 4, and we also have to subtract this, but of course we already have a 0 here, so we don't need to subtract. After performing all the subtracting operations, our final equation, our equations 2, this was 2, this was, sorry for the handwriting, this was our equation 1, this is 2, and this is 3. So our equation 2 becomes 0, from 0 minus 10 and 1, and our third equation will become a 0, 4, and a 1. If we subtracted this remains the same. Now that we have eliminated both our x's, we move on to eliminating. We are left with these two equations, and we move on to eliminating the y's. What amounts can we multiply these two such that our y's become, as when we subtract this equation from this, our y becomes a 0. can multiply this by a 4, giving us a minus 40, a 4, and this by a 10, giving us a 40, and 10 over here. Actually, we have to multiply this by a minus 4. Minus 4 will get a 40, then a minus 4 here. Then when we subtract these two, we'll get a 0, and minus 4 minus 10, that's a minus 14, leaving us with 2, 2, 1. This remains a 0, minus 10, 1, and this becomes a 0, 0, and a minus 14. Yeah, we performed those operations for the left-hand side. We also have to do the same for the right-hand side. Our left-hand side was this. Our right-hand side is B. We also have to do the same. We also had to do the same for B. Originally, this was 2, 2. This 2, 4, and 2. Here we had multiplied this by a 2 and this by a 3. So this became a 6 minus 6 minus 24. This remains a 2. So 6 minus 24, that gives us minus 18. And then for this, it remained the same because this was a 0. We didn't need to eliminate the x, so this was a 1. Then here we have a 2 minus 18, and we had multiplied this by minus 4. That's minus 18 with times a minus 4. That's a 72. We had multiplied this by a 10. So this 2, or this was a 2, this 2 that's a 20. 72 minus 20, that's a 54. So now that we have eliminated the x's here and the y's, let me write down our final equation, which will look something like this. This is a 2x plus 2y plus z equals to 2, and that's a minus 10y plus z equals to a minus 18, then minus 14 equals to minus 14z equals to 54. So from this is now where the back substitution comes in, whereby we can solve for this z. Then after solving for this z, we can substitute it into here. We get the y, then we substitute the y and z into this, and we finally get and we're able to get the value of x. Yeah, that will give us how to solve this equation using back substitution, using elimination and back substitution. And in interest of time, since my time is over, I'll stop there for today. Yeah. Any questions? If there are none, I believe the next person may proceed. If any of you prepared something, yeah, you can simply take over.
Hi, I'm going to be starting an introduction to probability, but since it's definitions, I'll just send the slides.
Okay. Samson, I saw you put something in chat. I don't know what that means. Yeah, you can feel free to text in chat to elaborate. When I was when I switched to the other desktop, I wasn't able to read the chat. Can unmute and elaborate or put it also in chat if you'd like. Question, Samson, Mark, do you have something for us today? You guys are still able to hear me. I see Samson has posted. Mine was regarding your workflow. Oh, Lubega has started presenting. Yeah, Mark, you may proceed.
So, good morning, everyone. I think everyone can hear me.
Yes.
So I didn't make a presentation, but I can share the resources that I used to get this information. Today, I'm going to introduce integration. So, integration basically it's a concept that we study in calculus to find the areas and volumes under curves or functions that we're trying to plot on graphs. So from this figure that we have, we see that the area under a curve, okay, using an interval between A and B, we've divided that area into like triangles or, yeah, okay. Sorry. I haven't introduced from the very start. Integration is what we use to find areas and volumes under curves. And we have different types of integrals. We have indefinite integrals. Indefinite are those whereby we don't have like an interval. So to cater for like constants, we add the c, yeah, and then we have definite integrals. That's why we have to like find area of volume under a certain curve, but the intervals between a and b. Yeah, then we have the integral techniques. Yeah, integral techniques, we have the substitution method, then we have the integration by parts. Sorry, the notes are a bit wide, so I think I'll just share them in the WhatsApp group. Should have made a presentation earlier, but anyway, I'll just talk about them. Yeah, so under use substitution, let me try to reach the right. Yeah, I think it's here. Under substitution, we let like a part of the function to be u, or we just assign it to u to simplify it. But then later when we are substituting the values of the intervals, we have to evaluate them back to like x or whatever was there initially, not u. And then yeah, then for the indefinite substitution, sorry, integration, since we are not given intervals, we do the same thing. We put the equation or the evaluation back into the original x from the u. Yeah. All right, I'm going to share these resources, and yeah, I think you read through them. Today I'd planned to cover integration, but unfortunately I hadn't prepared what to present, so it's a bit difficult. So maybe the next session I'll prepare slides, and also this was supposed to conclude on calculus 1, so next week I'll probably have to cover or introduce calculus 2. That includes series and yeah, the rest. I think we're all familiar with some of these things, so having to explain them, it's, I don't know, so it'll be more of time wasting. But yeah, as doctor said, we have to explain everything like it's new to us. But yeah, and as we see, some of these things require working out like the way Godwin was doing it, so having to go through the slides or sources as I explained also makes it a bit difficult. So I'm going to share these resources in the group, and yeah, I think that's what I have for today.
All right, thank you, Mark. Is there anyone else who has something to show?
just realized my microphone was off as I was sharing my screen. But I hope you guys can hear me.
Godwin, your volume is low. All right. I think we can end here for today. Yeah. Thank you guys for making it today. Yeah, thank you guys for coming. I think Godwin will share the recording later on. See you guys.